Now that we're familiar with acid and base reactions, let's take a look at how we actually communicate how strong an acid is and what that really means. So here is a chart I like that gives us kind of a baseline, and it's showing relative strengths of acids and bases. So kind of in the middle is water, acting as an acid is hydronium ion, and then its conjugate base would be water. So above this hydronium ion acid, we have our strong acids right here. And these include hydroiodic acid, hydrobromic acid, hydrochloric acid. Notice these are all hydrogens bonded to a halogen. Then we have sulfuric acid and nitric acid next. And these are each cases where our hydrogen is bonded to an oxygen and then to either a sulfur or a nitrogen. Below that, we have what we consider weak acids. Now, these are things like phosphoric acid, which is similar to sulfuric and nitric acid, and then it's a hydrogen bonded to an oxygen bonded to a phosphorus. Hydrofluoric acid looks a lot like our hydrogen bonded to a halogen, and this is our one halogen that forms a weak acid. And then we have carbonic and acetic acid, and these are going to be our organic acids, meaning that they incorporate carbons and hydrogens. And then ammonium and hydrocyanide and water at the bottom. So on the base side, we have then right here, the conjugate base of strong acids will be very weak bases because they're very unlikely to form the acid because it's so strong. And these are going to be the ions iodine, bromine, chlorine, sulfate or hydrogen sulfate and nitrate. And then as we get to our weaker acids, the weaker the acid is, the stronger the conjugate base. So again, the weaker the acid, the stronger the conjugate base. So water is a really weak acid, but its conjugate base is hydroxide, which is a very strong base. And when we say strong, in this case for an acid, we mean that all of the hydrogen bonds that are acidic break. And when we say weak, we mean that only 1% of the hydrogen bonds that are acidic break. This is very similar to a strong electrolyte for our strong acid and a weak electrolyte for our weak acid. We're going to communicate that strength, which is just what percentage of our acidic hydrogen bonds break, as an equilibrium constant. Now, this is the same equilibrium constant we talked about for reversible reactions. It has a subscript A, which means acid. So it's saying it's the equilibrium constant for an acid dissociation reaction. So that means we'll always have an acid, and our base will always equal water because of this being a dissociation reaction. Our conjugate acid will always be a hydronium ion, and then our conjugate base will be the conjugate base of our acid. So if we want to write out our equilibrium constant for this, remember we start with our products on the top right here. So the concentration of our two products are multiplied together, and then they're divided by the concentration of the reactants. Now we only include HA. We don't include water because it's in a different phase. Water dissolved in a water isn't actually aqueous, it's a liquid. So we're going to ignore liquids and solids in our K expressions. So we will make sure that we ignore the water concentration. And one way to think about this is that if we're doing these reactions in water, water is the solvent. So it's really hard to change concentration changes, or it's really hard to track concentration changes for something that we have so much of in the reaction vessel. So we'll see that the stronger the acid, the larger the Ka value. And what that's coming from is that the stronger the acid, the more of these bonds to the acidic hydrogen break. So if all of them break, we would have all product and no reactant left. And this would be very strong as an acid. And from our equilibrium chapter, we know that if our K is greater than 1, then our products are favored. So in this case, that's going to mean a strong acid. If K is less than 1, our reactants are favored. So this is going to be a weak acid, where not all of those bonds break. And we can do the same exact thing for our base dissociation reactions. And these we call KB, with B being representing base. But we go about it in the exact same way. Our base will react with water. We always do these as dissociation reactions, so the acid will always be equal to water in this case. And we always form a hydroxide ion typically from the water, and then the conjugate acid of our base. So we'll again make sure that we put our products concentrations on the top of the reaction and our reactants on the bottom, and ignore water. We also are always supposed to put the coefficients as the exponents when we do equilibrium expressions. But you'll notice we don't have any here. That's because our coefficients are all 1. And if they're 1, it's just itself, and we can omit writing it as an exponent. So because we have the products on the top of our equation, a large Kb that's greater than 1 means there are more products than reactants. That means a lot of this base, or acid-base reaction happened, and that makes it a strong base.